my name is Karn Prajapati and welcome to my video presentation for assignment 4 in AI and machine learning. In this assignment, I worked on building convolutional neural networks using the Cipher 10 dataset. The goal was to demonstrate overfitting and apply different techniques like regularization and data augmentation to improve our overall model performance. So I used the Cipher dataset, which consists of 60,000 color images categorized into 10 classes such as airplanes, cats, and trucks. So we have, as we can see that we have imported TensorFlow and NumPy, and I have loaded the data sets, and I used it. Then I converted the class labels using one hot encoded, which turns each labels into a binary vector. This is essential for our multi-class classification. Lastly, I split the original training data into 80% for the training and 20% for validation using our train test split from scikit-learner. And for our baseline model, the first model is a simple baseline CNN. It contains two convolutional layers followed by a dense layer. This model was trained for 30 epochs. As expected, it performed well on training data, but the validation accuracy plateaued and even dropped while validation loss increased. So this is the textbook example of overfitting, where the model memorizes training data instead of learning to generalize. And for our it's still working, so it will take some time as there is epoch 30. So let's go jump on towards our regularization and dropout. And to combat our overfitting, I modified the model to include L2 regularization and dropout layers. L2 regularization penalizes large weight in the model. I added it to the convolutional and dense layers using kernel regularization and regularizer for 0.01 seconds. Here you can see. And then this model had significantly better validation accuracy and a narrower gap between training and validation losses, which indicates improved generalization. So let's head towards our overparameterization example. And to demonstrate overparameterization, I built a deeper and wide CNN with layers like Conv2D 128 and then 256 and 512, followed by a dense layer with 1024 units. This is our units. This model had too many trainable parameters, which made it memorize training data extremely well. However, it did not generalize well. Validation accuracy was low and the loss was higher compared to the training loss. This proves that bigger models are not always better, especially when regularization is missing. And let's jump on towards our data augmentation. In this model, I introduced data augmentation using the ImageDataGenerator class in Keras. I apply transformations like horizontal flips, side rotations, and small shifts in width and height. This makes the model see slightly varied versions of the same image, which improves its ability to generalize. As shown in the graphs, this model achieved higher validation accuracy and was more robust compared to the earlier ones. So throughout the notebook, I used matplot library to create plots for training data, and this graphs clearly shows the effects of overfitting in the base and overparameterized models and the improvements due to regularization and augmentation. For example, in the regularization model, validation loss stays low and validation accuracy steadily increases, which indicates better learning. So for the final insights, I can say that in conclusion, this helped me explore the impact of various regularization techniques on CNN performance. L2 regularization and dropout helped me reduce overfitting. Data augmentation created a more diverse dataset and improved generalization. Meanwhile, the overparameterized model reinforced the idea that larger models are prone to memorizing rather than learning. Overall, combining these strategies helped me build a more reliable image classification model. Thank you so much for watching my video. I hope you found this breakdown helpful and informative.